Okay, so let's continue our discussion related to the overview of flexible electronics. Before we go into details of it, and last lecture, if you recall, we were looking at the overview of electronics, the field of electronics, and we said if you want to understand how electronics has developed over the years, one of the central themes is the scale of integration. Each one of the major milestones, if you look at the history of electronics, what it has done is enabled us to integrate more and more elements and thereby achieve more interesting and better functionality in terms of what you can do with the electronics here. And as a result, for example, the present electronics is, as we saw, is CMOS dominated. And even though bipolar was the first transistor to be invented, we find bipolar being used in very, very niche applications. If you look at, let's say, the number of ICs sold, bipolar would be, I don't know, 1 or 2%. Bipolar ICs would be 1 or 2%. So it's a very small fraction of. And what is the reason that is dominated by CMOS? Obviously, CMOS enables greater scale of integration, right? So we are saying scale of integration is the dominant theme. So CMOS obviously enables this greater scale of integration. But why CMOS as compared to bipolar? What is the reason? Okay, so you're right. Scale of integration is determined by two things. I mean, amongst other things, is determined by ease of manufacturing. Ease of manufacturing. Bipolar is more difficult to manufacture, being a vertical device. NPN is more difficult to manufacture, more difficult to interconnect and things like that, as compared to a CMOS kind. And the other one is power dissipation. We don't have, I'll not go into the details, we don't have CMOS-like bipolar circuits. Bipolar circuits, most of them that we have, will consume power under standby condition. When you have a logic 1 or a logic 0 or whatever, they'll consume power. And as a result, you would realize that when you're integrating millions of transistors, if power dissipation is high, then heat extraction and all that becomes an issue. And so that's the other reason why you find that electronics is dominated by CMOS, because of its negligible static power dissipation. All right, so we saw that along with MOS 1959, we saw 1959. Along with MOS, the TFT was also invented. TFT was also invented at about the same time as MOS, and both structures are field effect transistors. But we saw that MOS had superior characteristics in terms of performance, reliability, and mainly those performance and reliability, as a result of which all the electronics is developed around MOS. And TFT was sort of not really forgotten, but lost the battle in terms of the mainstream electronics. But we also saw that TFT, this is where we were in the last lecture, that this is an important part. As we said, whenever you are thinking of a new technology, this sentence is important to keep in mind. The principal applications of any new and innovative technology always have been and will continue to be applications created by the technology. And as we were discussing, the TFT survived as an important element, mainly because TFT is required to enable solid-state displays, large area solid-state displays. So this was, as I said, the initial thought of the people who invented TFT, that that if and when solid state displays are made, then because of large resolution, you would require the pixels to be arranged in the matrix form. And to selectively turn on a particular pixel, turn on or off, you would require a switch, meaning a transistor. And the transistor will have to be fabricated on such a display made on glass, large area display made on glass. The transistor will have to be manufactured on glass, and therefore we would require a TFT. Okay, so that was the thinking of at that particular time, why one would require a TFT. And because as I said, because of high resolution, we'll look at some numbers. Because of high resolution, the size of the switch is small, and therefore you cannot take a packaged MOS transistor and solder it there. You can't do that. You'll have to manufacture it on the glass itself. Okay, so that's why you would require TFT on glass. As I said, around the time when the TFTs were being developed, 1960s and 1970s, this LCD revolution was starting. And what you can see here, 1970 is your first LCD calculator, 71 is your LCD watches. So they begin to appear based on liquid crystal displays. And so now there was a technology available for making large area displays. Because for a display, what you would require is a light sensitive element. And LCD is that element. You can make an LCD cell opaque or transparent depending on the voltage that you apply. So because of the availability of LCD, a solid state display became possible. And as I said, the solid state display would have pixels. It would be arranged in the form of a matrix, and each pixel would be of something of this size. If I were to draw a display like this, let's say 2x2 display here, 2 rows, R1, R2, and 2 columns, C1 and C2. At the intersection of each, there is a, we'll look into displays later on, is a pixel. Is a pixel here. And each pixel looks like this here. Each pixel is a LCD cell, which is like a capacitor, but a LCD cell here. And along with it, there is a capacitor here and there is a TFT here. Right? So this is one pixel that you see here. Now, the reason why you have like this is, suppose you want a particular pixel to be, let's say, opaque or transparent. So what you do is, you turn this TFT on, you select that particular row, turn this particular TFT on, and allow this particular voltage to charge this capacitor here. Okay? So there's a voltage here, and let's say at that particular voltage, the cell is opaque. Right? And then when you turn this, when you turn this row select signal off, what happens? The TFT turns off, and the capacitor holds the charge and maintains the state of the LCD, whether it's opaque or transparent. Anytime you want to reprogram that particular pixel, you select the row again and pass an appropriate voltage and charge up the capacitor. So that's the basic functioning of the LCD cell. Any pixel LCD cell can be charged to any particular voltage that you want, and that voltage will determine the transparency of that particular cell here. All right. So what you see here is a display element, and now with TFT and LCD, because TFT was available, LCD was available, and so therefore they can be integrated to make a TFT LCD display here. And we'll go into these later on. What we can, through the, if we calculate the numbers, what you find is that a mobility of 0.3, 0.4 is more than enough to realize this particular system here. You don't require very high mobility. So the amorphous materials that were available, they could be used to fabricate the TFTs. So as I said, because the material is amorphous, so a lot of different materials were tried at that particular point of time, and most of these materials had problems of reliability. The materials would degrade over time, and finally a reliable material that was found was silicon itself. Silicon deposited on glass, as we said, is no longer crystalline but is amorphous silicon, and therefore amorphous silicon was used to make the TFTs, and the first commercial applications that came out of TFTs were these amorphous silicon TFT driven LCD displays here. Okay. And so TFTs then found a commercial application with these LCD displays here. So you can see these early years of early displays of TFT. Here, amorphous silicon address LCD display here. These are the first pictures here. Now, what you have to realize is that this LCD display that we are talking about is a IC on glass. The IC that you guys are familiar with is an IC like this here, made on silicon. but we said that what IC really means is the important word in IC is the monolithic, that you're integrating all the elements on a single substrate. That's the meaning of an IC, monolithic IC. So this display that you see here is an IC made on glass. And what are you integrating? You're integrating a transistor, you're integrating an LCD cell, and you're making a capacitor. So you're making all these elements on glass. And also all the wires that you see here, all the wires are also made on glass. This is what you do in IC. In IC, all the components are made, for example, on a traditional silicon IC, all the components you make on silicon, and all the interconnects, wires are also made on silicon. You interconnect them so that you have a complete circuit made on silicon. Same thing is happening here. So you can imagine common displays that we have. Let's say a full resolution display, full HD display will have 1080 rows into 1920 columns. So 1080 full HD, full HD resolution is 1080 rows and 1920 columns. So if you multiply them together, right? So this is the number of rows and number of columns and all that. And at the intersection of each row and column, I'm saying there's a pixel. So if you multiply them together, you'll get something like 2 million. 2 million pixels. And 2 million pixels means, let's say I'm using this particular LCD laptop here. And so there will be 2 million TFTs there, 2 million LCD cells there, 2 million capacitors there. So you can see that it's a, reasonably complex IC made on glass. The other thing, so it's IC on glass. The other thing is it's a large area IC. Large area IC. Traditional ICs, the focus on traditional ICs is to make them as small as possible. Because the smaller the IC that you make, because the size itself is not important in a traditional IC. The smaller that you make, the less silicon area, and therefore the cheaper it is. But here, the size is important. If you take display as an IC, in many of these cases, the larger, for example, if you're using a TV, the larger the display, the better it is, right? So sizes of importance here. Your interest may not be in reducing the size. So here is an example, a very different example of an IC, a large area IC fabricated on glass. So all of you are carrying a IC made in a very different way. All your cell phones and all that have, all displays are large area ICs. Except that it's made on glass here and made using TFT. So all of you are carrying TFTs in your pockets. So as I said, so TFT having been invented in 1959, TFT survived as a very important element. Without this particular TFT, none of the high resolution displays that you're familiar with, except for some simple displays, none of them would be possible. All right, so this is an important billions of dollar technology which is there. So TFT became an important element here. And you can see here, basically, TFTs were developed in 1980s. LCD displays were developed in 1980s and started entering into commercial space in 1990s with first laptops and all that you see with the TFT LCD display here. All right, so the two, with respect to flexible electronics, if you want to do electronics, realize that if you want to do electronics on a flexible substrate, and you want to do it by making electronic components and ICs on flexible substrate, and also realize that electronics without transistor is not possible, which means that if you want to do flexible electronics, it has to be driven by TFT. The TFTs will have to be fabricated on those flexible substrates. So this did happen on flexible substrates in 1960s, as we said, 66, 67 and all that. But it happened at the same time that CMOS was growing and the technology could not compete and there were no applications as such. But TFT as an element, as we said, TFT as an element on glass survived and enabled a very important application, which are TFT LCD displays. Okay, so this was about 1980s and that particular point of time. Let's switch gears and look at another element. Another element is the light emitting diode. Now, light emitting diodes, if you look at, although in principle, as a phenomena that when you pass current, light can be emitted from a semiconductor was discovered much earlier. But a practical LED happened at around this particular point of time, 1962, 63, using materials that you see here, gallium arsenide phosphide and 3,5 compound semiconductors, using those. So this is where LED was invented here. And there was very rapid progress, as you can see here. LED in terms of, one of the characteristics of LED is how much brightness of the LED. So the brightness would be measured in candela per meter square. We'll come to those units later on. The other one is efficiency of the LED, how much light comes out depending on how much electrical power, watts, lumens per watt. So what is the efficiency of the LED? So you can see here that LEDs, steady growth in LEDs starting from 1962 onwards that you can see here. The red one shows the red LED. So red LEDs, red and orange LEDs developed very rapidly. They were available. The problem was green and blue LEDs because they required blue LEDs, for example, because of the wavelength, it required a large band gap. Large band gap material like gallium nitride, people had lots of problems in making good quality gallium nitride crystals. And they had to wait almost, as you can see here, they had to wait in 1990s. So even though 1960, the red LEDs were invented, it's only after 1990 that you find blue LEDs really taking off. And so blue LED was really missing and green LED was also a problem in manufacturing. So imagine, so you have a red LED, but you don't have a green and a blue LED. So the LEDs could only be used in applications where you required maybe, some indicators and things like that. In all the instrument panels and all that, you see all these LEDs that are there. And even watches, you remember the LCD came out in 1970s, right? LCD came out in 1970s, LED is here, 1960s. So when people wanted to make the first watch, they started putting LEDs in them. So they were LED watches. But LEDs were, look at the efficiency of the LEDs. At this particular point of time, LEDs were very inefficient. So you use a LED watch and you have a battery and it would consume so much battery. So what happened was most of the time you would keep the LED off. So anytime you wanted to see see the time, you would press a button and then you see and quickly you would switch it off because it would drain the battery. So LEDs were there. But then the moment LCD came, LCD really killed LED for all display application. LCD was very low power because once you apply a voltage to an LCD and the LCD turns on and it's like a capacitor. It doesn't continuously consume power here. So LCDs basically, people really forgot about LEDs for any display application. LCD really took off here. Very early on, people could see that if you make LEDs, you could make very efficient bulbs. The traditional bulbs, we are talking about 60s, 70s, 80s, the traditional bulb where you heat up a tungsten filament and it emits light, the efficiency of that is around here, is about 10 lumens per watt, traditional bulb. So it was apparent that, one could see that there is a continuous progress. So it was apparent that LEDs would very quickly become more efficient than bulbs. And tube lights are somewhere here. You can see fluorescent lamp. And people could also see that, well, there did not seem any inherent limitation from physics as such that you could not get beyond, let's say, 200 lumens per watt or even 200 lumens per watt in an LED. So the path was clear that as you understand and develop better materials, better structures, it was clear that we could go to 100, beyond 100 and 100, between 100 and 200 lumens per watt. So it was clear that we could make very, very efficient light sources. But for a good light source, you need if you want to replace all these inefficient bulbs and also fluorescent lamps which require mercury, toxic mercury and all that, it was apparent that you require not just red, but you require green and blue. You require a green and a blue LED. To mix them, you require a white light. And that was missing, as you can see here. That was really missing. So there was a billions of dollars lighting market that could potentially be totally disrupted through LEDs, but that was not happening because of absence of red and green, blue LED. And then this discovery occurred here. And then after 1990s, you can see here blue LED really taking off, green LED taking off. Then white LEDs became possible. And then, from 2000 onwards, the lighting revolution really started. And now you're seeing all the LED lights all around you here. And it's for that reason that the inventor of the blue LEDs, they really got the Nobel Prize because of the large impact here. So this is what is happening in traditional LEDs. Note that when you have a light source, there are two principal applications that you're looking for from a solid state light source. One is lighting, right? For bulbs and all that, lighting is one application. The other one is, if you have LEDs, a red LED and a green LED and a blue LED, you have RGB, you could think of making a display using LEDs. Now, you may question, why would anybody want to make a display when you have an LCD display? Now, the problem with the LCD display is the following. There was nothing else at that particular point of time, so LCD had to be developed. The problem is that it's a relatively, you have to make LCDs, you have to make transistors, you have to make all of that. Initially, one major problem with LCD was that when you take an LCD and you look at it at an angle, viewing angle was very limited. If you look at it straight away, yes, you can see the nice picture. But if you sit at an angle and you see, the viewing angle was limited. So for TV, if a laptop's single user is working on a laptop, that's fine. But for TV, viewing angle, people sitting at different places, viewing angle was very important. So LCD had that one major limitation. The other one is LCD was a slow technology. Slow in the sense, the response time of the LED is slow. Because it's actually a liquid crystal. When you apply a voltage, the liquid crystal twists and then becomes opaque. When you apply a different voltage, the liquid crystal may untwist. So it's like a physical motion of a liquid crystal. So that makes it slow. If you want a LCD cell which is opaque and you suddenly want to turn it to transparent, it would take milliseconds of time to really turn transparent. It responds slow. Slow means that if you have a fast, in the sense of fast change in the picture that you're displaying, videos, then you would see blurring. So LCD had that particular problem, especially so you can imagine high resolution, gaming applications and all that, LCDs would have a problem. So LCDs had a lot of these difficulties that are there here. And the fabrication technology was also complex. So people knew that if you have red, green, and blue LEDs, the other one that is there here, if I put here, note that if this is let's say an LCD here, and behind the LCD, what you have is a light source. And then here is where you are seeing this one. So the light is going like this here, right? This light is what you're modulating. This light is what you're modulating. Now, even what happens is, even if you turn off the LCD, you apply a voltage to turn off the LCD cell, the light is still able to leak through. The turn off is not perfect. So the light, the light behind this laptop and all that, there's a light source. And so the light would still leak through. And so one of the other problem was that the black, maybe I should write it in black. The black, if you would read, the black was not a very good black. In the sense, because some light is still leaking through. So they always had a problem with this. The blackness was not good of an LCD cell. Or, I mean, if you're looking for just a display, then it doesn't really matter. But if you really want a very good display and you want very good black and bright white and things like that, on the other hand, the white was a very good white. You could have a nice white, color that is there. But the black was always a problem. Why? Because remember, this light is never switched off. This light is always on behind the LCD. All you're doing is the LCD cell is being programmed to switch on and off. And when it is off, it allowed still some light to leak through. And so the black was not very good. So people were always looking for, and they knew that we have these LEDs. The moment red, green, and blue LEDs became available, they were also thinking, well, we can integrate perhaps and make a display. But this is where it is a problem. Even if you have a red LED and you have a green LED and you have a blue LED, let's say, you have all these LEDs available. The trouble is, red LEDs, as you can realize, will require a different band gap. Green LED for emission will require a different band gap. Blue LED will require a different band gap, meaning 3 different semiconductors. 3 different semiconductors in general mean, all these semiconductors are crystalline. In general means 3 different lattice constants. Now, to make a display, you need both red, green, and blue. How do you make red, green, and blue on the same substrate? Suppose I use a gallium arsenide substrate. On gallium arsenide substrate, I can make a red LED. But to make a blue LED, I will have to deposit gallium nitride also. Now, gallium nitride has a different lattice constant compared to gallium arsenide. So if I deposit gallium nitride on gallium nitride becomes, there are a lot of dislocations. Lattice constants don't match. And so once you have dislocations, you have recombination, and gallium nitride LEDs don't work. So gallium nitride LEDs require different substrate. The red LEDs require different substrate. So how do you make red, green, and blue LEDs side by side in order to make a display? So you have all of them, red, green, and blue, but how do you make a display? So that was a problem.
Sir,
yes?
so the same problem with LCD also?
In
the LCD also?
Okay, in LCD, liquid crystal displays you are making, right? So liquid crystal displays you are making on glass itself. It's a liquid crystal sandwich between 2 glass plates, okay? What you do is, behind the liquid crystal display, you have a light source, a white light source. So you have a white light source. Let me put it like this here. So what does a liquid crystal really look like? So there's a light source. Light source, there's a cell, right? There's a cell here. And after that, there is what we call as color filter. Color filter, also deposited on top. So the light source goes in, the liquid crystal decides whether the white light goes through or not. And this color filter, if you have a red color filter or whatever, that allows a red light or a green light or a blue light. So you're getting red, green, and blue through filters. So you can see why LCD is efficient also, because you're passing only white light and you are allowing only red light to pass through. What happens to green and blue? You're just rejecting. And this light source is always on. So it's very power inefficient. Very, very power inefficient. In fact, the LCD, the laptop and all that I'm using, its efficiency would be 1 lumen per watt. And right now, the units may not make sense, but look at this one here, 1 lumen per watt. Your bulb, which is very inefficient, that bulb that you heat up, is 10 lumens per watt. LCD is even less. Most of the power, most of what you're feeding is all getting lost. It doesn't reach the eye. So it's a very inefficient one. So the light color is obtained through color filters. But here we are talking about a technology where we are saying we want red, green, and blue LEDs. Right? Red, green, and blue LEDs. And the issue is, how do I make this red, green, and blue LEDs?
In previous thing, if you want some other color than red, blue, or that, we should use multiple, right? In this one.
No. So what happens is, I showed 1 pixel, right? That 1 pixel would have 3 subpixels in it. Red, green, and blue. 1 pixel itself, 1 big pixel will have red, green, and blue. So depending on how much of red you pass, how much of green and how much of blue, you get different colors. That's why.
Three such structures should be there in 1 pixel.
Yes. In each one of them. So we are talking, yeah, red, green, and blue subpixels are there. And which is possible if you take your laptop and look at it with a microscope or whatever, small microscope, you can see the pixels in your laptop. You can see red, green, blue. You can see the screen with red, green, and blue there. Okay. So, but those are realized through color filters, separate films which are deposited on top of the LCD to get the different colors that are there. So here we are talking about. So the issue is LEDs are there, red, green, and blue. Why can't I make a display using red, green, and blue? Well, one way is you could take a red, green, and blue LEDs, separately manufacture them, and then put them on glass, solder them on glass, and make a display. So this is what we are showing here. There's a red, green, blue LED all soldered on glass. But note that the LEDs have been fabricated beforehand. It's like PCB manufacturing. The components have been manufactured beforehand. You bring them on a glass and then you put them on. Okay? Because of the size of the LEDs, dot pitch is only, separation between two LEDs, the center of one LED versus the center of the next LED is about 5 millimeter. But this technology has been changing. I'm talking about older, at that particular point of time, 70s, 80s, 90s, and all that. This one here. You could only get 5 millimeter. Now you can imagine a small cell phone display and with LEDs placed at 5 millimeter would be extremely low resolution. And it will simply not work. Okay? Even a very old phone, there's a Nokia phone, 2.4 inch, and very low resolution, 320 into 240. If we do the calculation of based on the height and the width of the display, and if we calculate, this low resolution display requires a pixel pitch of 0.05 millimeter. Note the resolution, 320 into 240. Resolution requires a pixel pitch of 0.05 millimeter. At that point of time, the technology, discrete LED technology, was 5 millimeter. So there was no way you could make a cell phone display. Similarly, if you take your present cell phone display, and you calculate your resolution is, let's say, 1920 into 1080, that kind of full HD resolution, and you calculate how many LEDs would I require and what would be the pixel pitch, you would find it very small. That's not something that you can actually make an LED and then stick it on glass. So the pick and place, the traditional method is pick and place. The traditional method of making electronics is pick a component, place it, and solder it. Pick, place, solder. So pick, place, and solder will not work. The only way you can make a display using LEDs is you have to make them on the glass itself, which means you have to make the IC on glass. So LEDs were available, but display was not possible with them. But now, interesting thing happened here that right at about the same time. So realize that, and so pick and place method will not work, and monolithic integration of red, green, and blue LEDs on an inexpensive glass substrate is also not possible, because you deposit any semiconductor on glass, it becomes amorphous, and those LEDs don't work. Amorphous gallium arsenide LED doesn't work. Amorphous gallium nitride LED doesn't work. It doesn't emit light at all. So that was not possible here. LED based displays have been around. You can see it in stadiums where, because it's such a large display, and so the pixel pitch is small. A pixel pitch is large, and therefore you can pick and place. So large displays in stadiums, or one of the famous displays on Wall Street, there is a whole wall which is a display. So large displays have been made using LEDs where pixel pitch is fairly large, so pick and place method can work. But smaller, more normal size of displays are not possible using this particular one here. The other thing, so what we realize is the following. If you were to make a display using LEDs, what you would have to do is, at each, let's say this is an LED, what you would require is, you would require LED to be turned on and off, right? So you would require a structure like this. See how this will work. For example, if I select a row And just for the sake of, I select a row, so I pass, let's say I put 5 volts here, right? 5 volts will turn the TFT on. And suppose in the column also I put 5 volts. So what would happen is, or let's say I put not 5, but so that you don't have an issue of how will it pass. Let's say I put 10 volt and I put 5 here. So what would happen to this 5? This 5 is here. 5 would go and charge up this capacitor, right? 5 volt would be here. And this is, let's say, 10 volt. So 5 volt, it turns this LED, this transistor on. And therefore a current flows and the LED is on, right? And now you can pass different amounts of voltage here, 5, 6 or whatever you want, and get different amounts of current that you want here. Now when you remove this 10 volt from here, what happens is the TFT is off. The TFT is off. The 5 volt stays there. Because the TFT is off, the 5 volt stays on the capacitor and thereby keeps the transistor on and LED stays on. So it stays on for however long you want it to stay on. At any time you want to turn this red LED off, you select this particular row, you apply, let's say if you want to turn it off, put 0 volt here, the capacitor would discharge and the LED will turn off and will remain off for whatever time you would like. So if you were to make a display using LEDs, you would have to make a TFT, 1, 2 TFTs, you would have to make a capacitor, you'll have to make an LED, you'll have to do all of that and integrate them on glass itself. Because the resolution is so high, you cannot do pick and place. So you'll have to make all these things on glass itself. So then it was, it's apparent that if ever you want to make a LED-based display on glass, you would require LEDs to be made on glass itself. Otherwise, TFTs on glass were always, they've been there. So you would require LEDs also to be made on glass. Without that, it won't be possible. So at this particular point of time, if you go and look at it here, the time when the conventional LEDs were starting, organic LEDs also were born at that particular time. Organic LEDs, meaning using organic material. Okay, so let's look at that particular aspect here. Organic LED. So this is the first LED that came out is a material called anthracene. So, anthracene would be, for you to recall your chemistry, benzene is 1 ring and then 2 rings and 3 rings. You can have anthracene and 4 rings, tetracene, 5 rings, pentacene and all that. So anthracene is a organic material. And so what they found, note that at the same time that normal LEDs were discovered, what they found was that if you take an organic material and you apply a voltage across it, you got light out of it. So traditional things were PN junctions, right? LEDs were PN junction, holes and electrons and all that. Here, they took this organic material, applied anode and cathode, 2 metals, and they saw light. And very interestingly, what they saw was blue light. Blue light coming. Blue was very difficult to obtain. 1962, 1963, they got blue light out of it, out of an organic material. So this should have been a revolution, except that this LED required 100 volt. It required hundreds of volts to work. Right? And what they were using is, you see here, 10 to 20 micron. This was a crystalline film. This was a crystalline film, very thin crystal of anthracene. And they put anode and cathode and they saw light coming out of it. But because it's so thick that you see here, 10 to 20 micron, and because the mobility of carriers is very, very low, it required very high voltage. Very high voltage, because at very high voltage, because the resistances are so large, then only you get significant current, then only you get significant amount of light. So blue light was seen out of it, but the voltage was 100 volts. And it was very quickly realized that we have so many different organic materials. You see in nature, all the colors that you see here in flowers and all that are all organic pigments. So it was apparent that unlike traditional semiconductors where you have maybe gallium nitride or a handful of materials with that kind of a band gap. In nature, we have so many organic materials which will give you red light, green light, blue light. I mean, there's no issue. There's so many different organic compounds. And so there should be no issue of obtaining red, green, and blue. All right. So it's for that reason that you see here a interest developed in making organic LEDs. But so it was clear that if you make, but you see here is 100 volts. So what they tried to do was, they said, okay, so this is 10 to 20 micron thick. Let's make the organic semiconductor thin. Now, thin, suppose I want it half a micron. Or let's say thin means to really bring the voltage down from 100 volts to, let's say, if I want to bring it down to 10 volts, because the mobility is so small, just for the sake of argument, let's say I require 200 nanometer of thickness. 200 nanometer thickness I want. Now, 200 nanometer thickness, how do you get a 200 nanometer thick crystal? You can't get that. Crystals are by the way they are grown and all that are thick. So 200 nanometer of crystal, you can't get it. But what you can do is, you can take this material anthracene, and these are highly volatile materials. So you can heat up anthracene, it would evaporate. And so if you take a crucible, put anthracene into it, heat it up, and you put your glass on top. So anthracene would evaporate and will go and stick to the glass. So you can form a 200 nanometer thin film. Very nicely you can form a film. But what would happen to that film? Amorphous. So that's what they did. They wanted to bring the voltage down, and so they made very thin films of anthracene, other materials also, organic materials, very thin, but they became amorphous. And as they became amorphous, what happened was mobility became even low, and efficiency of these things also became very low. So this is where organic LEDs were. Organic LEDs in principle were there, but very high voltage here. All right. So this is where organic light emitting diode was also born at the same time. So you can see TFT was born at the same time as MOSFET. TFT was forgotten except for LCD displays. OLED is also born at the same time. Around the same time that you see here, this one. But the problem with the OLED was, so you have now a red LED, which is nicely, efficiencies, look at that, developing. And you have an OLED whose efficiency is very, very low, extremely low. Why would anybody use a very low efficient OLED? All right. So this is where this particular OLEDs were up to about 80s or so. But the potential was clear. If you could somehow make, using an organic material, an efficient OLED, right? Then, because this is an organic material, it's clear that you need to make it using an amorphous material. Very, very thin material. So using an amorphous organic material, if you can make a nice LED, then you can make a full display. Because there are lots of organic materials, so you can make a green LED, blue LED, red LED. Note that because they are amorphous, no lattice matching, none of those things were there. Right? So that's where these strong interests were. And this is where finally very few groups were working and breakthrough was achieved here. In 1987. This particular group, Tang and Van Slyke from Eastman Kodak Company, they reported an OLED. We'll go into these things later on. They reported, the important point to note is they reported an OLED which worked at, note this, 10 volt, reasonable voltage, 10 volts, and look at the efficiency, 1.5 lumens per watt. I told you LCD efficiency itself is 1 lumen per watt. So it's at reasonable efficiency. Brightness, well, your laptop and all that, cell phones and all, will have a brightness of 250, 300 candela per meter square. So enough brightness, enough efficiency, enough dry voltage. This was a real breakthrough using an organic material. Organic material, and what did they do? Look at the structure. It is on glass, and they, without going into the details, they deposited all these organic materials on glass. Underneath is what we call as ITO. You will hear this word again and again. ITO, indium tin oxide. It's a transparent semiconductor. Transparent conductor, you can call it. Okay? So it's a transparent conductor. On top you have a metal. So the light comes out from this transparent conductor here. So it's an organic material deposited on glass and gives you this kind of a performance. 10 volt, lumens per watt, thousands of candela per meter square. Because it was the first LED developed, so stability and all that was poor. Okay. Now, so the first LED that these guys made were green, but very quickly they showed, well, you can make a red because there's so many different organic compounds available. You can make a red, you can make a blue, and you can deposit them side by side and thereby make an entire display. So the display started emerging in 1990s and all that. Displays started emerging based on organic LEDs. So organic LEDs then, so breakthrough occurred in 1987 and you find 1990s. So look at the time span, also realize the time span from, so let's take 1990 as the development of organic LEDs. And in your cell phone, when did it arrive? Maybe 4 or 5 years ago in your cell phone. So look at the gap, 10, 20, 30, almost 25 years. So from an invention to eventually get into your cell phone, a lot of challenges have to be met, have to be solved to finally get into your cell phone that we are all carrying now, about 20, 25 years. Quantum efficiency means that, see, you are passing current, right? You're passing electrons and holes. So what you would ideally want is, that you would want is for every electron hole pair, so every electron and hole should recombine and emit a photon, right? So what it says is for 100 electron hole pairs, only 1 photon is coming out. So 1% efficiency. But note that 1% efficiency is enough to give me 1.5 lumens per watt. So for many of these, at least display applications, you don't require very highly efficient. The other very interesting thing here is the materials. This would be shocking to you that I can have a LED with which I can make a display now. With this LED, I can make a display, right? What is the mobility of these layers? This would be shocking to you. The mobility is around that. 10 to the power minus 5 centimeters square volt per second. With 10 to the power minus 5 mobility, I can make a reasonable light emitting diode for an application. 10 to the power minus 5. So this is where I think we carry certain numbers in our mind, 1,000 and 500 and things like that. They are required for some applications. For an OLED, we'll do the calculations and show it to you that you don't require very high mobility. You don't require very high mobility, and therefore these amorphous materials that I'm depositing on glass, they have these low mobility, but they're okay. They're sufficient. They're sufficient to give me enough light and enough efficiency to compete with the existing technologies and make a full display. All right. Now, the other thing that comes in, so how is OLED contributing to growth of flexible electronics? So you are seeing an emergence of organic light emitting diode. Why? What are they trying to do? To make a display on glass. And the idea behind this display on glass is that eventually this technology would be much simpler because you're taking glass and you're depositing organic materials, much simpler in terms of fabrication than an LCD. The other one is, each one of these LEDs that you see here, I can turn them off. I can turn off, and what would happen? You will get a perfect black. There is no light source. You will get a perfect black. So they realize that with this LED here, you can get a perfect black, you can get a simpler way of manufacturing, and so this is potentially a very good display technology here. But then the other interesting thing that comes in here is the following. These organic materials that you see here were initially deposited on glass. But then the issue is these materials are amorphous. What prevents you from putting it on plastic? Because note that these materials, how do I deposit these materials? The glass is held at room temperature and you evaporate a material and it goes and sticks to the glass. So there's no high temperature step where this substrate is being subjected to high temperature, so you can deposit it on plastic here. So it was apparent then that you could make it because this is amorphous, just like LCD was, TFT was amorphous, and therefore you could put it on any material. Similarly, organic material is also amorphous, so you could put it on any material. So you could get a flexible and all those kind of display also. So the moment you work with amorphous semiconductors, it opens up that you can deposit them on a large variety of substrates. On metal, plastics, wood, cloth, you can deposit them on all of these things in principle, okay? And thereby have lots of interesting applications that are there here. So now what you're saying is there's a re-emergence of flexible electronics. The flexible electronics that started based on TFT sort of died down, was forgotten because there was no application. But with the growth of organic LEDs, now people realize that we can make these nice displays that you see here. Now I'll come to that. It's not just about flexibility that, you may say, who wants a flexible really display? But then note that traditional displays are all glass. And if you take it and drop it, it's gone, fragile. Plastic, you drop it, doesn't happen anything. Nothing happens to it. So the other one is, even if you don't care about flexibility and all that, it will be very robust. Cell phones regularly break, but if you make a plastic display, that will not break, okay? The other one is, glass is much more heavy. This would be much more lightweight. So when you make let's say a large TV, and if the TV is made on a plastic, it would be much more lightweight as compared to something made on glass. So there are all these other advantages that would come when you change this particular substrate that you see, okay? So what you're seeing is an emergence now of re-emergence of flexible electronics based on this organic LED. Now, once the organic LEDs were invented, note that to make a full display, I require an LED and I require a TFT. So till that particular point of time, the TFTs were made using amorphous silicon. This was the dominant technology. Now, amorphous silicon, what was it on? Glass. And this amorphous silicon on glass was a relatively high temperature process. They would heat up amorphous silicon and deposit on glass. So this was a high temperature process. High temperature process, and people realize that because this is a high temperature process, requiring temperatures of around 300 degrees Celsius or so. So glass can tolerate that. High temperature meaning not that high, let's say 300 degrees Celsius. So glass can tolerate that. But if I want to do it on plastic, plastic can only take maybe 100 degrees Celsius or so. So I can't do it on plastic. So I can't do amorphous silicon on plastic. And therefore, if I were to make my display fully on plastic and other substrates, I would need a new TFT technology also. So then, since LEDs had been made using amorphous organic materials, an interest in transistors, TFTs made using organic materials also started. And you find that, people reporting interesting transistors here. An all organic, soft, thin film transistor with very high carrier mobility. Now, when you note the word very high carrier mobility, please keep in mind they are comparing with amorphous materials. They're not comparing with silicon, right? So note that they're talking about amorphous silicon giving a mobility of around 0.1 to 1, and they're talking about their transistor giving a mobility of around 0.46. So they're saying, well, mostly you get 0.1, but here is 0.46. So it's a high compared to what people were obtaining with organic earlier. Remember, organic LED mobility, I quoted a value of 10 power minus 5. So organic transistors also, people were getting a mobility of 10 power minus 3, 10 power minus 2. So these guys are reporting a mobility of 0.46. Now, why is this mobility of 0.4 is important? Why? Because now, using this organic TFT, you can replace the amorphous silicon. Amorphous silicon TFTs had a mobility of around 0.5 in LCD displays. So now you can replace amorphous silicon with an organic TFT, and thereby make a complete display using organic TFT and organic LED, and thereby a complete flexible display here. So you can see here, these guys are writing. So mechanical flexibility. This is 1990, a very promising field is thus opening for organics, more especially because chemistry allows an almost infinite variation of electronic properties of this thing here. So unlike traditional semiconductors where you have a handful of semiconductors, here they said, I mean, we have hundreds of thousands of compounds available. The problem here is problem of plenty. The problem in traditional semiconductor is problem of scarcity. Why did blue LED did not develop? Because they had only gallium nitride. Gallium nitride was giving them so much problem. Right? If I had lots of other materials, I would have quickly abandoned gallium nitride, gone to another material. There is no other material. So crystalline semiconductors, there are only a handful of them available. But with the moment you go to organic and amorphous, you have a large variety of materials available. And therefore, in fact, that's what they're saying, almost infinite variation of electronic properties of molecules and materials that were there. So you want any energy gap, the organic chemist will give you that energy gap. You want 2, they'll give you 2. 2.1, 2.2, 2.3, 2.4, anything you want, they'll give it. They'll attach one side chain, one methyl group, one alkyl group or something they will attach, and they'll give you that much energy gap. So, I mean, a large, wide variety of materials is available here. So it's because of that also, people became interested. Now I can make LEDs. I can make transistors. I can do now these interesting things with organic materials. And what you find is a growth of emergence of organic electronics. A new field is growing based on organic materials. And I already talked about OLED in 1987. At about the same time, they made a photovoltaic cell, organic solar cell, with an efficiency of what? 1%. In 1986, 1% efficiency solar cell. It's a major breakthrough because before that, the efficiency of the organic solar cells was around 10 per minus 2, 10 per minus 3, that kind. So it was very low. And more than that, the number, they showed a path that, well, you have 1%, but if you follow this particular path, the efficiency can be steadily improved. Now, when you look at 1%, you should compare with what is the alternative technology. Is the silicon photovoltaics? Everywhere around you have silicon photovoltaics. What is the efficiency that you get? 20 to 22 is like in the lab. Actual, module efficiency, we are talking about, let's say 18%. Right? So 18% efficiency. But then we are talking about, let's say, look at this 1986. The silicon solar cells were very expensive. You won't find them anywhere. I mean, except for a few isolated places, they were too expensive to be used. Why are they too expensive? Ask that question. Why? They're still very expensive, right? Why are they expensive? Silicon solar cells, they're made of, well, you have to make it on crystalline silicon. Crystalline silicon, and that too you have to make it on highly pure crystalline silicon. Large area. So, it's because of that people realize solar cells were invented in, again, 1950s. The same time that transistors were invented, silicon solar cells were also invented at about the same time. But people realize that for solar cells to really, make a dent in the market, in the mass market, the costs have to be brought down. So very early on, people also started looking at, can we take glass? Glass is a very cheap substrate. Can we put some amorphous materials or something and make a cheap solar cell? So people have always been looking for an alternative to silicon solar cell. So here is OPV being reported at 1% solar cell. Remember, this is the first report, 1%, and where in the laboratory? This is 1986, and I'm talking about, let's say, 2019. Where has organic photovoltaics ended up is about 17%. 70% in the lab. So 1986, steady progress has been made, and about 17% in the lab. Silicon in the lab would be about 24%. And this is 17 or 18% now. Organic solar cells are also available. And we don't know where they will. It's not clear. For silicon, it's very clear they're never going to exceed 25%. There are physical limits from physics that they're never going to reach beyond 25. They'll always be less than 25, okay? So 24 and all that here. These have reached 17%. We don't know where they will end. There are other materials that have reached perovskites and all that that have reached more than 20%. So based on these organic materials, what you're seeing is here is OPV, a breakthrough in OPV, OLED. So you can do all these with nice organic materials here. So these are materials, OPV and OLED that you see here, these ones, they were made using materials like anthracene and pentacene and things like that, small organic molecules. And typically what you do with these small organic molecules, you evaporate them. So the technology for manufacturing them was through evaporation, vacuum evaporation. These ones were also happened here. People could show that they can take polymers. Polymers, and note that, now focus on these. This, and this. These three. First this, 1, 2, and then 3. So what happened was, polymers have always, people have thought of polymers, plastics as insulators. They don't conduct, right? 1977, you see a breakthrough. A breakthrough where what they did was they took polymer, polyacetylene, and by doping it, they made it conducting. So they took plastic and by doping it, they made it conducting. And how good a conductor? Well, how good is copper conductivity? How do you measure? Rho, right? Rho of 10 power minus, let's say 6 or 7 ohms centimeter, right? Resistivity of copper. Now imagine polymer, they could dope it and they could reach 10 power minus 4 to 10 power minus 5 ohms centimeter. This was like metallic property. So they took an insulator and added something to it, doped it and all that, and they transformed it into a conductor. A plastic became a conductor. This was a major breakthrough in 1977, and then obviously because of this breakthrough, they got a Nobel Prize in around 2000. Polymers became conductors. Then this work in 1990, they showed that they took a polymer film and they applied voltage to it and current flowed and all that. They showed that polymer film can emit light. Then they showed polymer film, you could make a diode out of it, and polymer film can act as a solar cell. So now using polymers, you could do, polymers now are not just insulators, but they are conductors. And they are semiconductors. You could make LED, you could make PV, and you could make TFT also. I've not said that. You could make a TFT also. So using polymers, you could do all of that. And what was very interesting about polymer is that polymers are in solvent. They're liquid. So what you could do is you have a polymer, take conducting polymer, right? So you have a liquid. And what you could do is you could take liquid, let's say on glass, put some few drops of liquid on glass and spin it. And what you get is a nice thin film of this particular polymer. And so you can get 100 nanometer thin film of conducting polymer. Very simple way of manufacturing, and you could get a thin film. You could get a thin film of LED, a thin film of polymers, a photovoltaic cell, through a very simple technology. You don't require vacuum evaporation and all that. You have to take it in crucible, put it in a vacuum and all that. You could just do it by solution processing. So the importance of polymers is solution processing. Your starting thing is a solution. So you find that this new field which is emerging because of all these breakthroughs that you see in 1977, 86, 87, 1990, 1995. So you find a new field is emerging, which is called organic electronics, organic or polymer electronics. And the new field is all based on amorphous material. Amorphous material, and it can all be done on plastics because the temperatures required are very, very low here. So what you find is a new field, this re-emergence of flexible electronics. That now I can do all these interesting things. See, earlier flexible electronics was only TFT. And it couldn't compete with MOSFET. But now you have all these OPVs and OLEDs and all these other things as a result of breakthrough in organic electronics. So what I would say is 1990s, you are seeing a re-emergence. 86, 87, and all these things that you see here, a re-emergence of flexible electronics as a result of breakthroughs in organic semiconductors here. So what is the, I'll stop at, what is the, large vision of the flexible electronics? The vision of flexible electronics eventually is a complete system on plastic or paper. In silicon, you would hear the word SoC, right? System on chip. So here we don't have system on chip. Chip is a silicon chip. We have system on paper or system on plastic, SOP. And so the idea is that, note that I've already shown you that we can make TFTs and we can make diodes, and if time permits, we'll see. You can do all of that, resistors, capacitors, everything you can make. All the elements that are required for electronics you can make. Not only that, you can make LEDs, displays. If time permits, we'll show you. You can deposit films on paper, and you can make loudspeakers also. Loudspeakers by depositing films on this here. So you can make a lot of, because we're talking about amorphous, so and all these films and temperature, gas, pressure, any of those sensors that you can make. Not only that, photovoltaics have also shown you. And battery also people have made on paper and plastic and other things. So what we are saying is all the elements that you can think of for doing electronics. What are the elements for doing electronics? TFTs, diodes, resistors, capacitors, LEDs, sensors. You require a power source, battery. Everything can be made on paper. Now, note that this is something even more ambitious than even on silicon. For example, with silicon, all that you can do is electronics. If you want to make a complete system using silicon, what do you have to do? You have to take electronics as chips. You have to add maybe a separate display, and you will have to add a separate battery. Right? It is still a discrete integration, eventually on a PCB. So silicon will always remain at that. You will have ICs made out of silicon, you have something else made out of display and something else made out of battery. And here, potentially, you could make everything on the piece of plastic using monolithic. So it can go way beyond silicon. You can make the battery monolithically. You're not taking a battery and separately adding a battery to it. No, you can make the battery on plastic. You can make the sensors, you can make electronics, you can make actuators, you can do all of that. So literally, in fact, system on chip is not the right word. They don't have a system on chip. The complete system, if you look at a cell phone and all that, is on a PCB. Right? Here you can literally have a system on plastic. Everything on the plastic itself. One single plastic sheet, and you could do everything on it. And so literally, this is what, now what people have done is they've shown elements of it. They've made sensors, they've made TFTs, they've made this, they've separately photovoltaics and battery. I'll show you later on here. So what it is doing is, flexible electronics is basically saying, I can make monolithic ICs on any substrate. That's what it says. So in a way, it's saying it's, people who are very fond of flexible electronics would say it's liberating electronics from a crystalline substrate. Traditional electronics is bound to a crystal. It's saying, well, now you can make ICs on any substrate. You can make it on glass, plastic, paper, using any of those other things that are there. So, you've heard the word ASICs, right? What do they stand for? So here also, this is the word that I have coined. Here also we are making ASICs, but what are these ASICs? Any substrate IC, right? on any substrate, you can make an IC. So it's also an ASIC that you can make, but on virtually any substrate that you want here. Okay. All right. What are the applications? We'll not skim through. So one of the prominent applications of this particular field is what you see is a display. And keep in mind, a display is a large area monolithic IC. That's what it is. Okay. Large area monolithic IC. So we've discussed that. So that's one application here. Electronic skin. Now, electronic skin is required for several applications, robotics, for example, and also prosthetics. When you don't have a limb and you're talking about artificial limb and artificial hand and things like that, prosthetics is another one. So there, if you want to make an artificial skin, now what you require is skin will have large number of sensors. At least for something to be called a skin, it should have touch sensitivity, pressure sensitivity, and also it should have temperature sensitivity. So what you're talking about is a large array of temperature and pressure sensors fabricated on a very thin substrate, like a very thin plastic film, right? To be called a skin, it has to be extremely thin. So here, this is what we have is a very thin plastic substrate that can be put on hand or whatever. It can conform to the surface of the hand and has a large area of pressure and temperature sensors. But this is what you'll see when you have a large area of pressure and temperature sensors. How do you read one particular sensor? How do you read one particular sensor's data? You require a transistor also. So these are all pressure, temperature. So to make an artificial skin, you require temperature sensors, pressure sensors, and TFTs, all integrated there. Okay. So this is an example picture of an artificial skin. You can see here they have FETs, and we'll go through these later on, FETs and pressure and temperature sensors that are there here. So electronic skin is another major application, okay, that you could do. Another interesting application, banknote electronics. Right. So when the new notes came out, some of you may have heard that there's a chip there, right? All that, that there was a chip or somewhere hidden. There was no chip, of course. But then why were people talking about it? The chip could be used to prevent counterfeiting. So now, but the chip can be removed and embedding it in, a silicon chip, embedding it in a banknote and all that is a complicated process. Here we are talking about taking paper and actually, making electronics on the paper itself. On the paper itself. And then once you do that, this electronics can contain all kinds of information that is there, which can be read by bringing a reader into contact with it. Okay? So this is something that cannot be peeled off. You cannot really remove and add and all that. It is made on paper itself. Okay? So these can have a lot of applications. You could have things printed on passports and all kinds of things to prevent anti-counterfeiting here. Let me stop here, and there are more applications. We can look at it later on. Let me come to some of you who are more interested. We'll come back here. All right. What will the course look like? So there are 3 parts to this particular course. Once we are done with our introduction, then one of the dominant technology behind flexible electronics is organic semiconductors. And these are amorphous semiconductors. So what we need to do is understand amorphous semiconductors. Understand amorphous semiconductors in the sense that how does current flow, how does injection occur, how do you make contacts, because that's one of the main technologies. Organic semiconductors, nanoparticles, nanotubes are the semiconductors. So we'll spend a lot of time spending on the physics of these materials. The next part is how do we take these things and make, so we'll spend some time on LEDs and solar cells and transistors. How do we make these things using amorphous material? So that's the principles and physics of organic materials and devices. The other part is how do we fabricate properties of flexible substrate, printing technologies and all of those. That's the other aspect of it, the actual manufacturing aspects. The third aspect is the applications. And the applications which we would concentrate on are basically the first line, array-based applications like displays, artificial skin, and those kinds of applications here. And so this is where, these are the 3 major blocks of this particular course. Often what happens is we end up talking a lot more about this here. We start off with this, and these fields are so large that to study amorphous or organic semiconductors in some depth takes a lot of time goes into that. So often most of the course revolves around this, and then a couple of lectures here and a couple of lectures here. So I would like to do things differently, spend a lot more time here also, but let's see how it goes. Learning material, class lecture slides I will share, and from time to time the journal papers. Okay, there is no textbook as such for this particular field, and so based on these two.